Okay, so let's think this run-up solutions. And now we will have our next keynote speaker. So it's Patrick Liu from XPeng. So Patrick is the director, principal engineer at XPeng. So he leads several perception teams in San Diego and Silicon Valley in the US and Beijing and Guangzhou in China. Also, he designs, develops, and delivers perception features that kind of enable critical functionalities for XPilot, XPeng's autonomous driving solutions. So talk title for Patrick is The Practice of Mass Production Autonomous Driving. Okay, so let's welcome Patrick. Yeah. Sorry about the technical difficulties here. Oh, me. Okay. It's okay. Good to go now?
Yeah.
Okay. Awesome. Yeah. Well, thanks everyone for coming here. I'm Patrick from XPeng Motors. And today I'm going to talk about the practice of mass production autonomous driving in China. For those who are not familiar with us, XPeng Motors is a electrical vehicle manufacturer. We firmly believe the great potential that autonomous driving would bring to the human society. So since the very creation of the company, bringing cost-effective autonomous driving solution to the market has been at the core of our business strategy. And what is shown here is the lineup of our vehicles in production. And at the center of it is XPeng G6, our latest release. It is a compact SUV. And we are a public traded company in both the New York and Hong Kong exchanges. Autonomous driving is a challenging task, and even more so in China. And China is perhaps one of the places that are most challenging even for a human driver, let alone autonomous vehicles. And we can take a look at this from three different perspectives. First of all, for dynamic objects, and the second is the static road topology. And the third, we have a bit of a difference. Sorry, just give me a second. Try to get this done. And third, it's a little bit hybrid. We have a traffic signal. Because traffic signals, they're typically static in geometry, but dynamic in semantics. And I will quickly overview the dynamic and static challenges, and we will do a deep dive in the corner cases of the traffic signal. So for dynamic objects, and especially for VRUs or vulnerable road users, they can take on a variety of different shapes and poses, and they appear at places where we don't typically
for human to figure out what's really going on. Actually, it's a vehicle fully loaded with tree branches. For a static road topology, this is also my favorite image of a static road structure. And this intersection really took the road design to extreme. It's almost look like a screenshot from a sci-fi movie, but actually it's a real place where we can observe from Google Earth. If we zoom in a little bit, we will see there is a piece of interesting road elements, and that is perhaps unique in China. It is a left turn waiting area. And they are initially designed to increase the left turn traffic throughput at intersection, allowing more cars to go through the intersection within one cycle of traffic lights. And you can even find academic papers about it, about its design and about its effectiveness. But it's also very obvious that this could cause confusion for even novice human drivers and let alone autonomous vehicles. And turning left at such an intersection involves a two-step process, and both involves some traffic light pattern shown here, and which requires some high-level understanding of the semantic meaning of traffic light or traffic lights. And I'm only showing the very typical traffic light pattern here, but they could be more complex, and sometimes even involving traffic lights that are specially designed for this left turn waiting area, which we will see later. Now let's take a deep dive into the traffic light. As we mentioned, the traffic lights, they are a bit different. They pose their own challenges because they are static in geometry, but dynamic in semantics. The recognition of traffic lights are challenging for two different reasons. And first of all, we have to recognize all the traffic lights in the sensor data. For example, here, if my human object detector is correct, we have 6 different traffic lights here. And second, out of all the traffic lights, we have to figure out which traffic light we should really pay attention to. This requires the correct matching between the traffic light to the traffic lanes. And also here we see a special type of traffic light. If you look at the left part of the image, it is a traffic light specially designed for buses. And we have to correctly recognize them for 2 different reasons. First of all, for the autonomous driving vehicle, because we are not a bus, we need to correctly identify it in order to ignore it correctly, because sometimes it may carry information that are conflicting to the traffic light that we should really pay attention to. And second, if there is really a bus nearby and we want to predict its maneuver, then we need to match the traffic light status to that bus correctly. And traffic light for buses, they may take on a variety of different forms. And here's some interesting examples. First of all, they can have different LED letters, the BRT, bus, SRT, or even simply a letter B. And of course, they can take on a variety of different Chinese characters. And they could also feature a little cute icon of a bus profile. And last but not least, we have traffic sign modifiers that are associated with these traffic lights. And for these ones, we have to identify both the traffic light and also the modifiers in order to correctly match them together, to make the semantic mapping. And here is another complex example. It's a multi-bulb. Typically, for a traffic light you see on the road, you have a 1x3 or 3x1 traffic light, and only one light bulb would light up at one time. And for special cases like this, you will have multiple bulbs functioning at the same time. And for these, we have to correctly figure out the location and semantic meaning of each light bulb individually. And here is another example. But here, in addition to this little building in the middle of the intersection, that's interesting. We also see additional numbers here. They are countdown timers before the next color change. And typically in North America, we will see these countdown timers a lot for traffic signals that are designed for pedestrians on crossroads. But these are actually for vehicles. These timers, this timer information, if used correctly, they can really improve the smoothness of the ride. And these are some corner cases of different formats of countdown timers. They could be on standard display, such as the first one, and they could also be integrated with the rest of the traffic light. For the first one, we have to detect both and matching them together. The display format could be different, could be having a leading zero, such as 02 shown here, or simply a letter, simply a single digit 2. And they could have different fonts, some of them more artistic than the others. Last, we can also have countdown timers in the format of a progress bar. And typically this is animation with the progress bar become shorter and shorter before they change to a full progress bar of a different color. And this could easily win the most innovative award for traffic light. But you can imagine this is a nightmare for perception engineers. And the last, we talked about the left turn waiting area earlier. And here are also some different formats of them. They could be in 2 different large categories. For the icon ones, these are typically also an animation where the lights gradually light up, guiding the vehicle to that waiting area. They could also be on text form. Some of them are in LED displays or in printed traffic signs. And there is no standard pattern of the text either. So in order to do this correctly, you have to do OCR and a bit of natural language processing to extract the exact semantic meaning. So despite these challenges, we still managed to deliver the best-in-class autonomous driving solution in China in mass production. And what is shown here in the SR display or surround reality display here is the perception results from our onboard platform. And we can see we can detect a variety of different 3D objects. And we can also detect some of them. We can also detect the other semantic features in detail, such as turn signal light, if you pay close attention to it on the left-hand side. And for static road elements, we see the road boundaries in red and also the driver space in gray. And note that this is not a demo video. This is actually a recording from a couple of days ago on one of our mass-produced vehicles without any aftermarket modification. I would like to highlight several milestones in the development of XPeng's autonomous driving solution. So over the past 2 to 3 years, we have released, we are the first in China to release a highway pilot system, the highway NGP or navigation guided pilot, and also the valet parking solution, VPA, and the urban driving solution, city NGP. And very recently, we started releasing city NGP to Beijing, so it's covering all 4 top-tier cities in China now. Note that these solutions basically sets the product experience standard for autonomous driving in mass production in China, and really cements the leading position of XPeng in this field. Note that all these 3 solutions I mentioned about are single stack solutions, meaning that depending on where you are on the highway, in the city, or in the parking lot, the underlying technical stack is different. Earlier this year in 2023, we started releasing the first version of our single stack solution, XNGP. It is built upon our next generation BEV or bird's eye view perception architecture. So both the BEV architecture and also the single stack solution it powers are some of the efforts we do at XPeng in order to achieve end-to-end autonomous driving solution. But before we dive into the details of XNGP, why do we need end-to-end in the first place? So here I'm drawing a little bit curve here, and in order for any practical engineering problem, in order to get to a solution fast, we typically have to do divide and conquer. That means we break a problem into smaller pieces until they are relatively well defined and easy to solve. The problem with this is that the more components you break the problem into, the more likely you'll get stuck with the local optimum. This is also echoed by the 80-20 rule, meaning that you can get to 80% of the performance with about 20% of the effort. So the benefit of divide and conquer is that you can get to a practical solution fast with about 20% of the efforts, but then you get stuck with the 80% performance ceiling. In order to get out of the local optimum and break the performance ceiling, we typically have to consider multiple components together and jointly optimize them. And we do this again and again, breaking performance barriers again and again before until we reach an optimal solution. So the final curve of technology evolution looks like a series of sigmoids stacked on top of each other until we reach the end-to-end and global optimum. There is another aspect of this, in order to get the 20%, the last 20% of the performance, we have to invest a lot more efforts. So bear in mind that all of us who gathered here in this end-to-end workshop are perfectionists who are not willing to give up the last bit of 20% performance, despite the fact that we might invest more efforts into this. So in a classical autonomous driving stack, 2D images are fed into perception module, and they would generate 2D results from multiple single cameras. And these results are passed down to a module called sensor fusion. And sensor fusion module reasons between all these 2D results and lifts them to 3D. And the 3D results are then passed down to downstream modules such as prediction and planning to generate the optimal control for the ego vehicle. Single cameras typically only contain partially the information of the objects and the environment we really care about. So binding them together requires a very careful adjustment of the fusion logic. And we have a lot of brilliant sensor fusion engineers working at this hard problem at XPeng. Essentially, we are doing backpropagation through engineer's head. This sets of logic very hard to create and maintain, and sometimes they even fail at very complex urban environment. So alternatively, we could also resort to this BEV perception paradigm, which combines the two components together and greatly simplifies the fusion logic. And at XPeng, our BEV architecture, we name it XNet. And XNet is essentially our first attempt toward this end-to-end perception stack. Here on the demo video on the right, the little red car in the middle is our ego vehicle and is going through an intersection. And we can see we can detect the 3D environments and both the static and dynamic very accurately around the ego vehicle. We started experimenting with BEV architecture about 2 years ago, the same time that academia picked interest in this area. And after many iterations, we finally settled on the architecture on the left. So we extract image features from multiple cameras with conventional, convolutional neural network, CNN backbones, to get multi-scale image features. And then these image features are then lifted to BEV space through a view transformer. In particular, it's actually a cross-attention module. And the multiple features from multiple timestamps of this in BEV space are then fused together with the help of ego pose to both spatially and temporally to get to this final fused feature. These fused features are then decoded into dynamic objects and static environments. The XNet is not only our first attempt to the end-to-end perception, but also it gives great promises to reduce the hardware cost and promotes the mass production of autonomous driving. The great ability to detect to sense the static environment actually reduces the necessity to have a HD map. So both of these measures actually greatly reduces the cost and also ensures the high performance of the autonomous driving solution. In the training and deployment of such big model, there are multiple challenges. So first of all, in order to train such a big network, we need millions of multi-camera video clips, and they involve billions of objects to be annotated. And we did a quick calculation based on our human annotation efficiency. This will take about 2,000 human years. For our internal annotation team, which has about 1,000 people, this will take more than 2 years to finish, and which is obviously not acceptable. To train such a network, it would take about a year to do that on a single machine. And if we deploy this onto the NVIDIA Orin platform, which we have at hand, without any optimization, it would take about 122% of the GPU power. So we won't even be able to fit it onto one unit. To boost the annotation efficiency, we came up with our auto label system, which greatly increases the annotation efficiency. This reduces what used to take about 2,000 human years. Right now, only a little bit under 17 days. And on the left, we show some inner workings of the pipeline, and it's essentially an offline sensor fusion system. And on the right, you see this demo. And note that this pipeline is actually heavily based on LiDAR. And we also have a separate pipeline that are more vision-centric. And that vision-centric auto pipeline enables us to annotate video clips that are harvested from a customer fleet. This is super critical as it forms a data closed loop and ensure that we have a self-evolving perception system. And moving on to the model training. Initially, we said it'll take about 300 days to train this. So we optimized the large-scale model training from 2 different perspectives. First, we optimized the training scheme, and we did a lot of optimization work on a single node, on a single machine, such as the mixed precision training, and also some optimization of low-level operators that are hard to run or inefficient to run on the GPU. And second, we collaborated with Ali Cloud and built a GPU cluster with about 600 petaflops of computing power. And then we scale our training from 1 node to multiple nodes. With both of these efforts, we were able to boost the training efficiency about 600 times. Now we can cut down what used to require about a year down to only 11 hours. Note that as we add more data, we harvest more data from customer fleet, we add them to the training data set. So this number keeps increasing. So the optimization is actually an ongoing effort to make sure that we have we keep this under control. And finally, I think there was earlier there was an audience asking about the deployment of transformers. We were also faced with the same problem. If you look at the initial chart, profiling chart at the top, what is taking up the 122% of the Orin GPU power is actually the transformer module. In order to do this, in order to deploy this transformer more efficiently on the Orin platform, we completely rewrote the attention mechanism, and we were able to get about 3 times the speed up. Note that this co-design of hardware and software is super critical. But so far for us, we have to really optimize on the Orin, NVIDIA Orin platform. And then we ask ourselves, can we do better? So we did a pruning of the backbone, which achieved another about 2.6 times of speed up. And finally, by load balancing between GPU and the CPU, we were able to squeeze a little bit more out of the computing device. So what used to take about 122%, now we can finish that with only 9% of the computing power. And this gives enough headroom for us on the Orin platform to try out different architectures for different use cases. And now we have this XNet architecture in place. we're ready to boost the performance by data iteration by building this data engine. So corner cases are first identified on the vehicle, then configurable triggers are deployed to our customer fleet to harvest relevant data. And in the cloud, we do image retrieval, either based on image patches or based on the text in natural languages. So here we are able to actually tap into the recent progress of large foundation models, large language models, to really boost the efficiency of data curation and also data annotation. So with both the XNet architecture and also the data engine, we are able to build a scalable and self-evolving perception system. And finally, before we conclude, finally, we are about to release Highway NGP 2.0. And this is a single stack solution for both the highway and in the city. This allows us to put whatever what we developed in the complex city scenario onto the highway and improve the user experience. And essentially, we're powering point-to-point user experience with end-to-end technology. And our vision is to build a single stack end-to-end solution that can power autonomous driving for all scenarios. And if this vision excites you, please consider joining us. We have multiple available positions in Silicon Valley and San Diego and back in China. Thank you very much for your attention. Question from the audience?
So I have a few questions, but I'll just ask two. Could you talk about the ways in which you use bird's eye view modeling in your stack, the different tasks where it shows that you get improvements when you use bird's eye view. Some of them you can only do in the bird's eye view, of course. And the second question is you mentioned the transformers. So this is both the view transformer and the transformer. I'm reckoning the.
It is yeah. It's the pun not intended, but yeah, it actually acts as both.
Did you consider the ray casting based architectures that start and shoot with transformers, and why you went for one over the other?
Sure. Sorry, I didn't get your first question. What was the first question again?
I mean, an overview of what the applications of the bird's eye view modeling is, like for lane tasks and 3D bounding box detection. It was there in your slides, but
right.
Perhaps more concrete.
Oh, okay. Sure. Yeah. Well,
yeah, thanks.
No worries. Thank you for your question. Yeah, we use BEV architecture for right now. We're only for doing dynamic objects and static environments because currently we do have lidars on our cars. For general obstacle detection, we use the lidars. So that's, I guess that answers your first question. Yeah. Okay. And the second is that for the transformers, yes, we use the cross attention module to lift the images from image feature from image space to BEV space. So we actually tried different varieties of transformers. And even before transformers, we also used to use MLP. I think one of the winning solution used that. With MLP, I think is relatively, deployment friendly for hardware. And we also tried lift splash shoot. But at that, I know right now, I think there are some deployment ready solutions for lift splash shoot. But at that time, this is about 2 years ago. At that time, we did try both. And I guess we picked a transformer-based architecture for 2 different reasons. First, architecture, transformer-based architecture, at that time, we thought, and through ablation study, it gave us better results. And the second, we have 2 different teams working on this. deployment problem, and we finally cracked the problem of how to deploy transformers onto the device, and how to deploy lift splash shoot on NVIDIA platform at that time was not very clear to us. That's right. That's right. I think there's called BV pool E2 or something. Yes, that you can use. I think the one of the lessons we learned is that the architecture perhaps is okay as long as does not have any information bottleneck in it. What's really driving the performance is the large scale training and large scale annotation, and also the data closed loop through the data engine.
Yeah, thanks for the talk. It's very impressive. And I have two questions.
Mm-hmm.
The first question is that you mentioned about the auto labeling system, right? It's very good, but from my understanding, you are kind of labeling the other objects or lanes, something like that, with a larger multimodal network, right? Is my understanding correct?
Actually, yeah, here I'm only showing the auto labeling for dynamic objects. For static objects, actually, we do reconstruction of the scene and then we label on top of it.
Okay, great. But if you have some minor issues with the larger program, how do you fix that? That's my first question.
With what? Sorry.
Like some missing objects or some misdetections.
Oh, misdetection. I see. Yeah. Well, because this is an offline system, you can first of all you can do tracking, right? Non-causal tracking. Because you can leverage the power of hindsight. You can see the future, and typically what used to be an extrapolation or filtering problem now becomes an interpolation problem. Becomes much easier. And the second, you can leverage multiple different models, offline models. Essentially, you're doing an ensemble of different models, and that can also helps with the quality control. And finally, here we also have what's not shown here is we also have a auto QA process and always coupled with a human QA process. So the quality assurance is super important for this application.
Okay, thank you so much.
Yeah, thank you.
And the second question is kind of more high level. Is that how much do we like to push the end-to-end autonomous driving to? I see from your slides that the end-to-end you mentioned is mostly focused on the BEV part, right? But for the planning part, you hardly touch that. But I see that's a very important part of the XPeng autonomous driving, and I have actually tried that by myself. So how do you think of that?
Yeah, that's a very interesting question. I think for now, yes, we're pretty much limited the BEV or the end-to-end solution to both the perception and prediction. For planning, in my opinion, I think it's still pretty much an open research problem. We haven't converged the two. What's the practice, the interest, the researchers from academia and industry. I think they're trying different ways, and we internally we are also trying actually. And in my opinion, I think this is a very promising field. This is the last piece in order to get to this end-to-end solution, right? So to make it end-to-end differentiable, yes. I'll be glad to talk to you after this.
Thank you so much.
Very much for your presentation. I have a question. Are you using HD maps?
We do.
Okay. And if so, are you doing some change detection of the maps? Are you updating the maps to keep them fresh?
That's right. That's right. Yes, that's a very sharp question. Yes, especially in China, construction is working, is undergoing every single day. This is we have a dedicated team internally to work on that problem. And also, this is one limitation. I think one limitation or constraint of HD map. Not only the cost for each car, you have to pay some fee, and for how to maintain the freshness of the map is also a very challenging problem. And in order to detect and also to maintain this map up to date, I think BEV perception we just mentioned here, it would be a very promising solution, and we are working on that. don't have a very good answer to that. We're also exploring the possibilities, from perception and to even to prediction and to planning. There are multiple ways I think the perception system can output the uncertainty. For example, temporal uncertainty is one thing, and that is typically handled by sensor fusion. When you do some tracking, you see the tracks when they get unstable. That's one great hint that the perception quality might be subpar. And also, of course, there are some deep learning based methods you can directly output uncertainty as well. Aleatoric and epistemic uncertainties, if you know about these papers.
Yeah.
I think these are the two approaches that you can propagate these uncertainties for downstream to handle.
Thank you so much.
Yeah, thank you.
Thank you so much for this informative and presentation.
Thank you.
And I actually have two quick questions. So the first one is, according to the architecture you're going to figure out the left side of the XNet, it shows like the input only cameras. Did you use any other types of modality inside the XNet itself? And my second question is that it would be great if you could give us some insights about, how to orchestrate different kinds of modalities like camera, lidars, and how to, leverage the pros and cons between different types of modalities.
I see. Well, for the second, I'll perhaps answer the second question first. Think, camera and lidars and also radars, they have their distinct advantages, right? To me and internally, we really think that the correct usage of lidar, maybe I'm biased, is actually detection of general obstacles, right? For the objects that are not on the whitelist. For example, the car I showed with a lot of luggages on this, it's maybe really challenging for the 3D object detectors to pick them up. So that's really the use case, a really good use case of lidars. That's how we are using it internally. And the second, to answer your first question, is we actually only use cameras. It's a vision-centric system. The reason is that for all the other sensors, they are still rapidly evolving. For example, 4D radars, right? And also the radars, they keeps changing. The firmware also keeps updating. And also for the lidars in the industry is still rapidly evolving as well. The cost is coming down year on year. So we don't want to, if we fix them right now and into an early fusion stack, that solution would not be as scalable as of what we do now. We do a vision centric, or we do early fusion between multiple cameras, and then late fusion with the rest of the sensors.
Thank you so much.
Thank you.
Hi, thank you so much for the talk. I had a question on the data engine part. So you mentioned that you do text to image and image to image search. Can you describe, that process a little bit more? And do you retrain whatever model you use for this, for specifically the self-driving case?
I see. That's a good question. I think for now, the quick question is that right now we don't. We just use them as off-the-shelf tools to do that. And that's already enables us to do a lot of useful things. And I think fine-tuning them for our specific use case, especially our images may look a little bit different from the images on the web. I think that would be a very interesting direction to explore. Yeah, thank you for a suggestion.
Thank you.
Okay, so let's send Patrick in.